So, now, so we have seen that the HF goes as C some constant times Zukowski number power 2 by 3. This is one of the things, but this is actually non-dimensionalized HF by D. Okay, now coming back, the Zukowski number indicates momentum dominated jet if its value q star, if q star is more than 10 power 4, then it represents a momentum dominated jet. Okay, so this was indicated by McCaffrey. Now, q dot also represents the ratio of combustion energy to the nominal plume energy, because we have non-dimensionalizing this q dot heat release rate divided by the, this is like the energy carried by the plume. So, that this is the ratio. So, now we can also do this. When I say q dot, the Zukowski number, and I raise it to the power of 2 by 5, what I get is q dot divided by rho infinity C P infinity T infinity into root of G D into D square power 2 by 5. Here I can write this as q dot by rho infinity C P infinity T infinity root G divided by D. So, this q dot divided by this, which is q star, raised to power 2 by 5, represents a ratio of length scale. So, this by this, so it's a ratio of a length scale. So, observing that q dot power, so here we can say q dot power 2 by 5 is correlating a length scale, ratio of a length scale. The correlation for the flame height was given by STS dash, the correlation for the flame height was given by STS cat dash HF equal to 0.23 q dot power 2 by 5 minus 1.02 D. Okay, so you can see that the plume analysis leads to lot of important analysis and correlations. Okay, so now let us go for theoretical analysis of a plume. So, now going back to the schematic here. So, this is the base of the fire. Okay, that is a source, a condensed fuel surface or solid surface or liquid fuel surface. Now, when I just extend this, the plume edge, I get a virtual origin. So, that means I do not really care about the dimension of this. I say that this plume, because of the fact that this is very short length, this plume basically is generated by a point source which is located at a virtual origin below the fuel surface or finite dimension fuel surface. Okay. So, the theoretical analysis for a fire plume starts with the point source where some enthalpy is flowing or energy is coming out, and for theoretical analysis I have to do lot of assumptions. Now, so let us make this first an idealized plume. We are now talking about an idealized plume which is generating from a point source. Okay, and this is the edge of the plume. The solid lines which are drawn from the point source extending towards the Z is the edge. Now, we can see that simplifying assumptions ought to be invoked in this. Okay, now what are they? First one is the change in density within the plume is negligible. So, this is the plume edge. So, this is the plume area and this is ambient. Ambient density is rho infinity. Within the plume, the density is rho, that is it. obviously temperature varies in the plume. That means density also should vary. But one of the simplifying assumption is the density within the plume changes in a negligible manner. So I can say some average density, even I will not put rho bar, I will put say rho. Rho is the average density of the plume here. That doesn't change. Okay, now, but please understand that temperature will change, no? Temperature profile if you draw. So for that only we are now taking a velocity profile which is like top hat profile like this. So if at this station, so this is the z value. At this station, if you want to draw the velocity, it will look like this. Yeah, constant velocity profile. It will look like this. So top hat profile. But in reality, we saw a Gaussian profile. So here, if you go back, this is the realistic profile, velocity profile here, what we have shown here. But for theoretical analysis, at least initially, we will consider a top hat profile. Now, plume density is assumed as local ambient density. Buoyancy force is calculated using the difference between the ambient and the plume density. That's it. So, this approximation is called Bouusinesq approximation. Okay. So, when the see why we can invoke this is in the plume the temperature has reduced considerably, not like in the flame zone. So, the temperature difference also is decaying. Based upon the fact, at least for the theoretical analysis, we invoke this particular assumption. Now, so including radiation will be tough. So, radiation heat loss is neglected. So, as I told you, uniform and top hat profile for both velocity as well as temperature, we are assuming that only. Velocity of the air entering to the boundary. So, for example, I can say take any height and take a control volume at a particular height like this. Then the velocity of the air which is entering is V, that will be proportional to the plume velocity at that particular height. So, U. So, please understand U is a function of Z. So, V will be written as alpha into U. So, V also is a function of Z. Alpha is some constant, you can say. So, I have shown in the figure like this. Then the domain is symmetric. So, only one side we can analyze this. So, there is no oscillation in the radial or lateral direction. And again, please understand that due to the buoyancy force, this entrainment occurs. The pressure difference causes the entrainment to occur. So, let us not even worry more about the viscous effects. So, these are the simplified assumptions, may not be completely real, but at least it will give you some expressions for the velocity and temperatures along the height, and then we can correct it for the realistic conditions. So, that is the aim of this. So, Martin et al. Reported a work. Based upon the work, the mean flow variables are calculated by solving conservation equations for mass, momentum and buoyancy. Okay, we will have the conservation equations for these and try to solve the get the variations of this along the height, variation of u, t, etc. along the height. Now, the conservation equations: mass flow rate of the plume kg per second, okay, m dot p, control volume, take a control volume of height dz and radius b, that is called plume radius. B is the plume radius at a particular height z. So, height z, plume radius is b at that particular height. So, as I told you, go back here, this is the plume radius. I have just taken some edge and this is the plume radius at a particular height. So, the plume radius actually varies with the height. Okay, now mass flow rate of the plume can be written as rho density of the plume, which is not going to vary within the plume, into the average velocity of the plume into pi b square, that is the cross sectional area, that will be the mass flow rate. So this is the, I am saying this is the, so the flow rate comes like this. This is b, the radius. So this is the mass flow rate of the plume. So that is, so the area under consideration is pi b square. Rho, v, u, etc. are the quantities at the particular height. Okay, now at a particular z, m dot p z can be written as rho u z pi b z square. Now, increase in the mass flowing up to the differential element will be equal to the mass entering to the sides per unit height. That's it. That's a mass conservation. So, as the mass which is flowing out from a lower level to higher level, this is also added by the mass which is entering into the sides, correct? So, if you go back to this, so there is a mass which is coming from the bottom from this and goes out, and the mass which is coming to this control volume plus the mass which is entrained due to this air entrainment will be the mass which is going to flow out. That is a simple conservation term here. So, that is what. So, when you write that, I get this equation, d by dz of, that is the rate of change of the mass flow rate of plume with height will be equal to 2 pi b circumference into dz, that is surface area through which mass enters with a velocity of, or air enters with velocity of u. Do you understand? So, 2 pi b dz is the circumferential area through which a mass flux of rho infinity and v. Rho infinity v is the mass flux that entrains. So, this is nothing but the mass rate of air divided by dz. That's it. Do you understand? So, 2 pi b dz is the circumferential area through which air entrains with a velocity v. We have by this photo you can see this from the schematic. So, circumferential area is 2, this is actually b is the radius here. So, 2 pi b into dz, that is the area, into v is the velocity, into rho infinity. Okay, so combining this, the conservation of mass can be written as d by dz rho infinity u pi b square equal to 2 pi rho infinity b alpha u. So, d by dz rho infinity u pi b square equal to 2 pi rho infinity b alpha u. Please note that rho, because of the fact that the temperature difference is not very high, rho is approximately taken as rho infinity in this conservation equation. But for buoyancy force, the difference of this is taken into account. Do you understand? So, that is very important. So, here the rho is calculated as a function of the plume temperature. This rho infinity is calculated as a function of the ambient temperature. But in the conservation equation, you can see that the rho is replaced by rho infinity straight away. Here, rho u pi b square is written as rho infinity u pi b square. Okay. So, that is the approximation. As per this assumption, here the change in density within the plume is negligible as compared to the ambient density. That is all. The plume density is assumed as the local ambient density at a particular point. That is it. So, since the ambient temperature or ambient density is outside the plume is not going to be different, then we can make this. But to calculate the buoyancy force, the difference between the ambient and the plume density is taken, where the plume density is calculated as a function of the plume temperature itself. So, this is approximation which we are making to get this particular expression for the mass conservation. Next is simplify this, because you know that the ambient density is constant. So, Based upon that, I simplify this, get rid of the ambient density. D by dz of B square u equal to 2B alpha u, because now V is also taken as alpha u, correct? Here V is taken as alpha u. So I am getting this expression. This is called equation A, the mass conservation equation is simplified form, equation A. Now let us go to the momentum conservation statement. Rate of change of momentum through height dz equal to buoyancy force plus viscous forces, but this is now not included. So only buoyancy force is taken into account. So as I told you, to consider the buoyancy force, I will take the difference of density between the ambient and the plume. So rho is a function of the plume, average temperature of the plume. Rho infinity is a function of the temperature at the ambient. Okay, now what is the rate of change of momentum through the height d is d by dz of mass flow rate into velocity, m dot p into u, that is equal to buoyancy force. Now viscous force is not included. So buoyancy force is density difference into g. So this is the force per unit area into pi b square, that is the area. So now I substitute for m dot p rho infinity. Please understand that rho pi b square u into u, that gives the u square here. Instead of rho, I write rho infinity. So rho infinity pi b square u square equal to right hand side, same values come here, rho infinity minus rho into g pi b square. Now rho infinity is constant, so I take it to the other side. Okay, pi cancels, so I write this is the equation for me. D by dz of b square u square equal to rho infinity minus rho by rho infinity into gb square. Okay, now this is written in terms of density. This is the momentum conservation equation, but I can now change it to temperature based also. We will come to that later. Before that, I will see what is called the conservation of the energy. The heat flow, convective heat flow Q dot C at any height Z can be written as the mass flow rate of the plume into Cp into delta T. Okay, delta T is nothing but T at that particular height minus the ambient temperature, delta T. Okay, and within the plume, since we have assumed that the velocity or temperature will not change, we can say that the T variation along the plume radius will not be present. So T is a sort of average temperature. Do you understand? So for example, if I have a profile like this for temperature or velocity, I can also put a profile like this, where this is maximum temperature I get, T naught central line, but this is the average temperature. So both are same. The energy content in this profile, within this profile or this profile will be the same. So I can say that the T is the average temperature of the, not considering any variation in the lateral direction. Okay. So now the convective heat flow Q dot C can be 60 to 80% of the Q dot. So you have to understand the difference between Q dot C and Q dot. Q dot C is the convective heat flow and Q dot is the total heat which is released. Q dot equal to okay. So this is the thing. So from this I can get the energy conservation, but before doing that I will use the ideal gas law. Rho T equal to rho infinity T infinity. Now rho is plume density, which is dependent on the temperature of the plume at a particular location, and T rho infinity is the ambient. So now delta T is T minus T infinity, delta rho is rho infinity minus rho. You understand this? Both are positive because plume is at a higher temperature, ambient is at a lower temperature. So delta T is positive. Similarly, delta rho, since T is higher than T infinity, rho will be lower than rho infinity. So this is also positive. So now I can write delta rho by rho infinity as delta T by T infinity. So T minus T infinity by T infinity into T infinity by T. But one more assumption I invoke here. The T itself, when you see the plume where the temperature decays, T approaches T infinity. So this I take as approximately 1. So I can say delta rho by rho infinity will be delta T by T infinity. That's it. Like this very simple term. Now, writing delta T in terms of Q dot C from the energy equation and using the expression for delta rho by rho, the momentum conservation can be now. So I am now incorporating the momentum conservation and I am adding the energy conservation also into it. So here you can go back to the expression which we have derived. So this is delta rho by rho. Okay, so we add the momentum conservation written as d by dz of b square u square equal to rho infinity minus rho by rho infinity into gb square. Now d by dz of b square u square equal to gb square into delta t by t infinity. So now I can write this as q dot c g by going to this balance. Okay, delta t, correct? I am writing that as delta t by t infinity as delta t. I am writing as q dot c g here from this. Delta t will be equal to q dot c divided by pi b square rho u c p. So pi, because the b square cancels, rho infinity, instead of rho I am writing rho infinity u into Cp, and since I am dividing here by T infinity, I am also dividing here by T infinity. So this will be my second equation which combines the energy balance as well as the momentum conservation. So this is equation B. So equation A is the mass conservation, d by dz of b square u equal to 2b alpha u, and here the B will be equal to the momentum conservation where the energy is also incorporated. So here A and B are two ordinary differential equations, and the unknowns are the radius at a particular height, the plume radius and the plume velocity. That's it. Okay, now this can be calculated only when the convective heat loss is known or heat transfer, heat flow is known, correct? This convective heat flow, as I told you in the previous slide, can be taken as 60 to 80% of the total heat release rate. So Q dot is the total heat release rate and QC is the convective heat flow. So please understand that I am writing in terms of convective heat flow because this statement is based upon the convective heat flow, and an approximation there also can be done as the convective heat flow will be 60 to 80% of the total heat flow. So now, so once I know Q dot, I can get the value of Q dot C and I can solve A and B together to get B and U, correct? So now to solve this, let us assume B equal to some constant C1 into the location Z power M. Similarly, the velocity U equal to C2 into Z power N. Do you understand? So this is what I am trying to write everything, that the two independent variables are what? Z actually there is only one independent variable here, because we are trying to have no variation in the r direction. So, the r direction, the t or u is uniform, top hat profile you have used, no. So, the only variable is z. So, I write b, the plume radius, as c1 into z power m. Similarly, u as this. Now, plug in this to in equation A, d by dz. So, what is equation A? Go back and see once, b square u. So, instead of b, I have to put c1 into z power m, u equal to c2 into z power n. Do you understand? Similarly, here also b and u, we have to substitute those constants. So, c1 square is z power 2m, c2 z power n equal to 2 alpha. What is this? B, this is u. So, I am substituting this. Now, I rearrange this. C1 square, C2, 2m plus n, z power 2m plus n minus 1. So, differentiate this, I get this equal to 2 alpha C1 C2 z power m plus n. So, when you differentiate this, I get this. So, that I call equation C. Okay. That is the equation. Again, having what? Alpha is known to me, where some fraction of u, which is indicating generating the v here. So, v equal to alpha u. So, alpha is known to me, z at a location. So, that is the independent variable. So, C1, C2 are there in this, m and n also are there. So, I form one equation here. Now, same thing, b equal to C1 power, C1 into z power m, u equal to C2 into z power n. Now, using the equation b here, equation b, instead of b and u substitute that, then I get this equation. You can see that, okay. And this you differentiate to get this, and here I write the same thing. Now, I get this equation. Equating the power of z on both sides of equation, this is equation D I call. Okay, now go back to this is equation C. Now, z power 2m plus n minus 1 is there in the left hand side. Here z power m plus n is there in the right hand side. But since these two are in an equation, we can equate the power of z, because I don't know the values of m and n. So, if I equate the powers of z in the left hand side to the in the right hand side, I get one expression. Similarly, in this equation D also, here z power minus n is there in the right hand side, here z power 2m plus 2n minus 1 is there. So, if you equate the powers of z on both sides in equations C and D, I get the values of m and n, because I generate two equations now. There are two unknowns m and n. So, I get the values of m as 1, n as minus 1 by 3. Now, I substitute this in this equation. I get, for equation C, I get equation E, for equation D, I get equation F. Okay. Now, I have to solve for C1 and C2 from this. Do you understand? So, this is one of the mathematical approach where I try to put the both unknowns B and U as a function of Z, but having some power profiles, okay, some exponents, multiply with some constant. Okay. So, I get E and F. Now, equation E and F can be used to evaluate the constants C1 and C2 as C1 equal to 6 by 5 alpha and C2 equal to 25 by 48 alpha square q dot C g divided by pi rho infinity Cp T infinity the whole power 1 by 3. Okay, now I know C1 and C2. As per definition, I will now get the value of, so m, everything is known to me now. What is m? M equal to 1, n equal to 1 by 3. M equal to 1, n equal to 1 by 3. I know C1, C2. And what is the definitions what we have used? B equal to C1 z power m and u equal to C2 z power n. So, now I know C1, C2, m and n are known, minus 1 by 3 here. So, I substitute here and get the expressions for the plume radius 6 by 5 alpha into z. So, as z increases, so alpha is a constant, plume radius increases. Now, u, something which is dependent on the ambient properties, fuel property, etc. Okay, into, so this is constant, correct, into z power minus 1 by 3. That means velocity reduces as height increases. So, this is not accurate values, because even here alpha is not very much known to me. Q dot C is only taken as 60 to 80% of Q dot and so on. So, that means here also alpha square comes. So, these are estimates which actually says how the profile varies. Lot of simplifications like rho is approximately taken as rho infinity in this equation, but only for the biometric force it has taken, we have taken the temperature difference, that is rho infinity minus rho is a function of T minus T infinity, something like that we have taken. Second is how the profile, Gaussian profile is not taken into account, we have taken the top hat profile and so on. So, now these are the expressions I get this. Now, I go to conservation of buoyancy, which is d by dz of b square ug rho infinity minus rho by rho infinity equal to 0. Okay, this is the conservation of buoyancy. That means I can say that this term is a constant, b square u g rho delta rho by rho infinity will be equal to constant. Okay. So, I will talk about the solution of Plume tomorrow. I will stop here.